Hello, students, and welcome to our lesson on the rules of exponents. This is a lesson that, quite honestly, tends to give students quite a bit of trouble when they're first learning it, because it is a lot of rules I'm going to throw at you all at once. But I assure you that individually, all of the rules are quite simple. It's just having to put them all together that tends to give frustration. So throughout this video, what you're going to notice, by the way, there's multiple ways to do all these things. And so when you have so many rules, there's not always one right way to do each of these problems. And so a couple of the problems I'm actually going to do more than once, or at least show you a couple different directions you could have taken. So at first, I will just show you the way that my brain tells me to do it after years of experience. But I will also try to show you other methods that get you to the same place using the same rules, just in a different order. All right, so that being said, let's dive into all the vocabulary and what these rules are. We're going to start off with just what is an exponent. So the polynomial expression below has three parts that we need to be able to identify and describe. The 5, okay, this 5 in front is in front of the variable, and we call that the coefficient of the variable. Okay, so right here we have a polynomial expression. This is also just a term. Okay, this is one term, and it has a coefficient of 5. The number in front of the variable is a 5. The 4 up here in the top, that is a superscript. So if you're on a keyboard, the way you put that up there is by doing the superscript button. And this is called an exponent or a power. Okay, so we have 5x to the power 4, or to an exponent of 4. And then the x itself here, okay, we would call that variable the base of the exponent. So we have a base of x and an exponent of 4. Okay, base of x and an exponent of 4 with a coefficient in front of 5. So now we're going to be working with these words quite a bit in this lesson. So let's just make sure before we move on, the coefficient is the number in front of the variable, and the power or exponent is the number that is the superscript on top of the base. All right, so now let's talk about the rules. The first rule we're going to talk about is called the product rule. And the product rule is applied when expressions are being multiplied together. It states to multiply the coefficients and add the exponents with like bases. So a key here, by the way, is we need to have like bases. So we're going to take that for granted as we move forward. But if we don't have the same base, then none of these rules actually apply. Okay, we're going to see this phrase like bases in all of these problems, or all of these rules at least. If the exponents are not on like bases, in this case they're all x's at the front at first, then we can't compare them and we can't use any of these rules. In the next one, we're going to see that we have bases of both x and y, so we treat them separate. We do x's with x's and y's with y's. So just make sure you're always looking for like bases. All right, so what this rule tells us to do, the product rule, says that when we are multiplying expressions with like bases, we add the exponents. So for example, x cubed times x to the 5th is x to the 3 plus 5, which is x to the 8th. Okay, so usually I won't write out that 3 plus 5 because we can add numbers in one step. Okay, so we're just going to go straight to x to the 8th in that case when we're multiplying x cubed times x to the power 5. When I say cube, by the way, that means exponent of 3. Squared means exponent of 2, cube means exponent of 3. All right, the second example here shows us what to do with the coefficients. So in this next example, we have a coefficient of 3 and a coefficient of 2. So the product rule tells us to multiply the coefficients. 3 times 2 gives us 6. And then when we multiply the x terms, we add the exponents. So we're going to get x to the power 9 because we're doing 4 plus 5. Now, the reason we're allowed to do this with the product rule is because we have commutative and associative properties of multiplication, where we can actually rewrite this statement here as, instead of doing 3 times x to the 4th times 2 then times x to the 5th, this is the same thing as 3 times 2 times x to the 4th times x to the 5th. where I can then use the associative property to put parentheses around the first two and last two. So it's equivalent in multiplication to rearrange and reassociate values. So instead of doing the 3 here and the 2 over here, I can actually just put the 3 and 2 next to each other. And then I can also put the bases next to each other and then just apply the product rule on those bases. So the reason this rule works so nicely is because we have the commutative and associative properties that allow us to regroup and remaneuver or rearrange the terms. All right, next rule we have. The next rule is going to be called the quotient rule. And this is applied when expressions are being divided. It states to divide the coefficients and subtract the exponents. But we're only going to subtract exponents when they have like bases. Okay, so again, if we have a base of x and a base of y, we leave those separate. But when they're both the same base, then we can apply the rule. So in that first example, x to the 12th divided by x to the 4th, this is x to the 12 minus 4, where again, usually I won't write out the subtraction there, but this is equivalent to x to the power 8. So now it's very important to realize that we don't have to subtract in that direction. Okay, I do not have to do the number on top minus the number on bottom. I can also go the other direction if I want. So let me just show you what I mean by that. Instead of moving the 4x's up to the top and doing x to the 12 minus 4, it is equivalent to do instead move the 12x's down to the bottom, and then I would get 1 over x to the 4 minus 12, which would be 1 over x to the negative 8. So we can actually move the subtraction in either direction. I can either take these 4x's and subtract them from the x's on top, or I can take the 12x's on top and subtract them from the x's on bottom. But we're going to see later in this lesson that we don't want a negative exponent. So see down here, I have 1 over x to the negative 8. I prefer to have x to the positive 8 as my final answer. So although we can do that, and we will in some cases go top to bottom instead of bottom to top, we're going to actually do whatever keeps the exponent positive. Okay, so in this case, we wanted to move the x's up to the top because that kept a positive exponent, but that's not always going to be the case. All right, example number 2. We are going to divide the coefficients. So we're going to do negative 18 over 3, where that negative sign was in front, so I just leave it in front. Then we're going to multiply this by, we're going to subtract the exponents. So x to the 8th is next, and then y to the 6 over y to the 1 is going to be y to the 5, because I do 6 minus 1. If I simplify that, that's going to be negative 6 x to the 8th, y to the 5th, where all I'm doing is dividing the 18 and the 3, but including that negative sign in front. I'm subtracting the exponents on the x's to get 12 minus 4 is 8, and I'm subtracting the exponents on the y's to get 6 minus 1 is 5. But notice again, in this case, I was moving these variable terms to the top and subtracting them from what's above. Technically, I could also have subtracted the other way, but we always want to do whatever keeps positive exponents. So positive 8 and positive 5 meant I did it the right direction. We'll see examples later where we're going to be going the other direction. So just hold tight for that one. Okay, our next rule is called the power rule. The power rule is applied when raising an expression or a term to a power. Okay, so it's called the power rule because we have a term raised to a power, and it states to multiply all exponents. So now that might sound a little weird. It's better shown in practice. So for the first example, it's not really going to demonstrate it too well. The second example will demonstrate it better. So the first example, we have x squared to the power 7. This is equal to x to the 2 times 7, or x to the 14. So we multiply the exponent on the inside times the new exponent on the outside. The second one, though, is going to illuminate what students often mess up, which is the fact that when we have a product inside, we have to multiply the exponent on the outside times both exponents on the inside. And so in this problem, 5x to the fourth to the power 2, we multiply 5, or we raise 5 to the power 2. Right now, 5 has an exponent of 1. We just don't write the 1. But when we distribute that new exponent, we're going to get 5 to the power 2 and x to the power 8 because we do 4 times 2 for that exponent. But then we'll always simplify numbers. 5 squared is really 25, so we have 25x to the 8th. The reason we have to multiply the 5, or we have to raise the 5 to the power 2 like we did, is because if we write this out in a different order, so if I just take this over to the side, 5x to the power 4 squared is really 5x to the fourth times 5x to the fourth. Now, if I solve that the way I solved the one in the first example, so way up here at the top of the screen, then I would multiply the coefficients. So 5 times 5 is 25. And when I multiply x to the fourth times x to the fourth, I add the exponents to get x to the 8th. So we get to the exact same place. So all the power rule does is simplify this process of multiplying all the different terms together. So instead of having two of them next to each other, I can just write it as being squared and then distribute that exponent. I could have shown you that with the first example over here, x squared to the power 7, but quite honestly, I didn't want to write out 7x squareds. But notice that if you tried it, x squared times x squared times x squared times x squared, 7 of them, then you would end up adding all those 2's together, and they would add together to give you x to the power 14, just like what we got. All right, the next rule is the easiest rule. Okay, this is the 0 rule, and this is applied when an expression is raised to a power of 0. Anything to the power 0 is equal to 1 with one note except 0. Okay, so we're not allowed to raise 0 to the power 0, but we are allowed to raise anything else to the power 0, and in all of those cases, we will get 1. All right, so for our first example there, 9x to the power 0, this just equals 1. Because we have an expression to the power 0, automatically 1. The second example though, 9x to the power 0, where the 0 is only the exponent of the x, this is going to be equal to 9 times 1, where x to the power 0 is 1, but that 9 is just out in front, and so this equals 9. All right, so it's very important to realize what the exponent is actually on, because it's not necessarily on every term. In the first example, we would distribute this 0 to both things inside, so we'd be doing 9 to the power 0 and x to the power 0, which is 1 times 1. But in the second example, only the x is raised to the power 0. So now students often want to see a proof of this one, and it's very simple. Why does anything to the power 0 equal 1? Well, if we start with the number 1, I can write an equivalent expression that represents 1. So for example, if I have x squared over x squared, I know that that's something divided by itself. So something divided by itself automatically equals 1. Okay, well, we just learned rules of exponents for quotients. If I actually subtract the exponents for x squared over x squared, I would get x to the power 0, because 2 minus 2 gives me that 0. And so notice that x to the power 0 is equal to 1, but I never told you what x was. All right, so we can say that anything to the power 0 is 1 by just using basic rules of exponents. We know that something divided by itself is 1, and in this case, that something over itself is something to the power 0. So anything to the power 0 is going to equal 1. The only thing that breaks this is 0 itself. All right, last rule we have is going to be the negative exponent rule. So the negative exponent rule is applied when an expression is raised to a negative power. Any part of the expression with a negative power moves to the opposite side of the fraction to make the power positive. So what I mean by move is that it changes from numerator to denominator or vice versa. So in the first example there, 2 divided by 3, x to the negative 4, the x to the negative 4 can move to the top, and our new expression will be 2x to the positive 4 over 3. where all we do is take the thing with a negative exponent, in this case, the x, and we move it to the other side of the fraction. So x to the negative 4 in the denominator, when I move it to the top, it becomes x to the positive 4. And it's that simple. All you do is move it from numerator to denominator or vice versa, and it changes the sign. All right. Next, we have 8x to the power negative 3. If I move the x to the negative 3 to the denominator, remember that 8x to the negative 3 is really over 1. We just don't write the 1 when it's the denominator. This is going to be equivalent to 8 to the power, or 8 divided by x to the power positive 3. So when I move that x to the negative 3 down to the bottom, the new exponent is positive 3. It changes sign. All right, and we have one more rule of negative exponents. Okay, so a little bonus for you here. If you have a fraction to a negative power, okay, so let's say that we have x over y to the power negative 2. This is equivalent to y over x to the power positive 2. Okay, so the rule here is that negative exponents on the outside of expressions can change signs by doing the reciprocal on the inside. So now I'm going to put a step in the middle to show you why this is true. X over y to the power negative 2, we already saw that we would distribute that negative 2 to both things inside. So this is equivalent to x to the negative 2 over y to the negative 2. And then if I move things from top to bottom and bottom to top, so if I switch the places of these, then the y becomes to the positive 2 on top, and the x becomes to the positive 2 on bottom. So I would end up with y squared on top and x squared on bottom. And then you can see that I can pull that 2 back out to be the new exponent, so it's y over x all to the power 2. So the extra steps aren't necessary here. The important thing is that if you have a negative exponent on a fraction, you can write the fraction as its reciprocal, and that exponent changes sign. So we can show the steps in the middle, but really we just need to know this rule that a fraction to a negative exponent, when you flip the fraction to its reciprocal, that negative sign goes away on the exponent. All right, now we're going to do some practice, but first, a word of caution. There are no rules for addition and subtraction. So exponents do not change in that context. For example, 3x squared plus 4x squared is equal to 7x squared. Okay, we know this as combining like terms. So combining like terms. When we add together 3x squared and 4x squared, we get 7x squared. We add the coefficients and the variable and the exponent stay the same. All right, so when we're adding and subtracting like that, the exponents do not change. Similarly, 8x squared minus 2x, we don't do anything to. We actually just leave those separately because those are not like terms. And so we would leave those as is, and we wouldn't do anything to them. So we just leave it. So I'm going to write leave it alone. Okay, so just a reminder of combining like terms. Students tend to, when we get into this discussion of exponents, get a little bit confused with combining like terms. This is different. When we combine like terms, we only add the coefficients of terms that have the same exponents. But if they don't have the same exponents, we do not put them together. We leave them separate. All right, so now we're going to put all these rules together. In general, we're going to follow the order of operations, which is, please excuse my dear Aunt Sally, or PEMDAS if you prefer, parentheses, exponents, multiply, divide, add, and subtract. And also in general, simplified polynomials should not contain negative exponents. So I mentioned this earlier when I showed you different ways we could end up with negative exponents, but it's very important that when we get to the end of all our expressions, we make sure nothing is negative in the exponent category. All right, so if we get a negative exponent in the middle of the problem, that's okay. We just have to use the rule of negative exponents to rewrite it. All right, so now let's go ahead and solve these. When we look at number 1, we have 2xy squared to the power 2 multiplied by another expression. The first thing we need to do is distribute this exponent to the three terms that are inside. Okay, so when we have product inside and an exponent outside, we distribute that 2 to all three things inside. So we're going to have 2 squared, x squared, and y to the power 4 because x and 2 both had exponents of 1 before. And so we multiply both of those exponents by 2. And then since it was y squared inside, we multiply by 2 to get y to the 4th. Now we have the expression you see there. We're going to go ahead and multiply the coefficients. So if we multiply 2 squared, that's 4. And 4 times 3 is going to give us 12. X squared times x squared is going to give us x to the 4th. And y to the 4th times y cubed is going to give us y to the 7th. So all in all, we end up with 2 squared is 4 times 3 gives us 12. And then x to the 4th, y to the 7th. All right, number 2. We have 3z squared times b to the power 2 divided by 3ab cubed. So similar start to this one. We're going to handle the exponent on the outside of the numerator by distributing it to all three things inside. So when I do that on top, I'm going to have 3 squared, z to the power 4, and b to the power 2. And in my denominator, I didn't do anything, just 3ab cubed. All right, so now we can do a little bit more simplification. We have 3 squared on top and 3 on bottom. If I divide those exponents, if I divide those numbers, 3 squared is 9, and 9 divided by 3 just gives me 3. And that 3 is in the numerator because it was 9 on top and 3 on bottom. I have z to the 4th, but no other z is in my problem. So I'm just going to leave that z to the 4th exactly where it is. There's no like base to combine it with. All right, then I have b squared on top and b cubed on bottom. Because I have b squared up here and b cubed down here, I want to decide, should I move the b squared to the bottom or should I move the b cubed to the top? The way you decide is whichever exponent is bigger. Okay, so because b cubed, 3 is bigger than 2, I'm going to move the smaller one to the bottom. So I'm going to take this b squared term and move it down here. And when I do that, b cubed minus the squared, so I'm going to do in the denominator, I'm going to subtract. 3 minus 2 just gives me 1b on bottom. Okay, I'm going to write that one in red just to make it clear where it's coming from. I have b to the 3 minus 2 in the denominator there. All right, and then we only have one a in the problem, and that a is in the denominator. It's just going to stay put. So now if I simplify that b term, I'm going to end up with 3z to the 4th over ab, where I just have 1b in there because 3 minus 2 on the exponent gave me b to the power 1. So now there's an alternative way to do this. If instead I simplified this first part here to be 3z to the 4th over a, and instead of moving the b squared to the bottom, I move the b cubed up, I'll get b to the 2 minus 3 on top, which would simplify to be 3z to the 4th b to the negative 1 over a. There's nothing wrong with taking the b cubed and moving it to the top like I did to have b to the 2 minus 3 here. But when I get b to the negative 1 in this next step, I wouldn't be done with the problem. I would still need to take this b to the negative 1 and move it to the denominator. That way I end up with b to the positive 1 because we don't want any negative exponents at the end. Okay, so this is what I was talking about with negative exponents. If we make our decisions wisely, so move the b squared to the bottom because 3 is bigger than 2, then we don't have any negative exponents to worry about. But if we make the wrong decision and we move the b cubed to the top, then we're going to end up with b to the negative 1, and we'll have one more step to move that b back to the bottom to make it positive. So I recommend you do it the first way we did it, which is to move the b squared down to the bottom instead of moving the b cubed up to the top. All right, next one. We have 4pq to the 5th over r to the 4th to the power negative 3. What I'm going to do is the rule of negative exponents I showed you, where when you have a fraction raised to a negative exponent, we can flip the fraction to make it its reciprocal. So r to the 4th over 4pq to the 5th. And now I'm going to write a new exponent of positive 3. Okay, so I flipped the fraction. I did the reciprocal of what's inside, and then I made the exponent positive instead. That is a very powerful rule because it saves us a lot of steps here. The alternative was to distribute this -3 to everything inside, and then I'd have a whole bunch of negative exponents floating around. The way I did it instead is I made this exponent positive, so now when I distribute this exponent, because we now have to distribute it to the top and all 3 spots on bottom, we're going to end up with all positive exponents. So in the numerator, r to the 4th to the power 3, we multiply 4 times 3 to get 12. So we have r to the 12th. And in the denominator, 4 to the power 3, we'll simplify in the next step. Then we have p to the power 3 and q to the power 15. A lot of students get confused on why it's p to the power 3. It's because the p currently has an exponent of 1. We just don't write the 1 on that exponent there. But we're multiplying 1 times 3 to get p to the power 3. All right, and then just to simplify this, we can go ahead and say that it's r to the 12th over 4 cubed is 64, and then p cubed, q to the 15. All right, a couple more here. For number 4, we have a -2 that we're going to have to distribute as an exponent. So we're going to distribute this -2 to everything inside. That'll give us 2 to the -2, p to the -2, and q to the -6 when we distribute it. But then we still have the first part of the problem, which is 4p cubed q to the 4th. So now we could immediately deal with these negative exponents, but it's actually going to work out to be easier if we use the product rule first. Okay, so I'm going to treat the numbers or the coefficients separate from the variables for a second. So I'm going to put the 4 on top from the original 4 on the left, and I'm going to put 2 squared on bottom, where it became 2 squared down here because I took this 2 to the -2 and I moved it to the denominator. So I'm moving this one all the way down to here. The variables, though, I'm not going to move around yet. I'm just going to multiply the p cubed times the p to the -2. That'll give me p to the +1, because it's 3 minus 2 there, so that'll give me p to the 1. And q to the 4 times q to the -6 is going to be q to the 4 minus 6, which will give me q to the -2. So this leaves me with a new expression where I have 4 over 4, because 2 squared on bottom is 4. And then I have p to the 1, q to the -2. So now I'm going to simplify this. The 4's are going to cancel because 4 divided by 4 is just 1. And the q to the -2, I'm going to move to the denominator. So I'm going to end up with p on top and q to the power +2 in the denominator, where this ends up actually being pretty nice by the end of it. Okay, p over q squared, a lot of this simplified out. But a couple key steps in there. We have to make sure we distribute this -2 to everything inside. We have to make sure that if we have negative exponents, we bring them to the bottom. So I took this 2 to the -2 and moved it down to the bottom. And we just have to be careful that we don't make any trivial mistakes along the way. So when I was doing 3, or p cubed here, times p to the -2, I was adding the exponents. So I did 3 plus -2, which is this 3 minus 2 here. And then I did q to the 4th times q to the -6, where again I add the exponents. So I do 4 minus 6 as my new exponent. And because q to the -2 had a negative exponent, I just made sure to move it down to the denominator. All right, a couple more. On the next one, we have negative exponents again. So I'm going to distribute on the top, and I'm going to distribute on the bottom. In the numerator, we're going to have 9 to the -2, x to the -6. And in the denominator, we're going to have 3 to the -3 and x to the -12. So now I could very reasonably try to simplify this all in one step, but I think it's going to be easier if we make everything positive first. So instead of trying to even think about what all this actually equates to, I feel it's easier if we make all our exponents positive first. So to do that, I'm just going to flip this all upside down. So if I move the 9 to the -2 to the bottom, 9 squared goes down below. And if I move the x's with it, I have x to the 6 down below. So I'm literally just taking this whole fraction and I'm flipping it upside down. So the 3 cubed is going to be on top where it becomes positive 3, and x to the 12 also goes on top where it becomes positive 12. I personally find this much easier to work with because I don't have to think about the negatives now. In order to simplify this, I have 3 cubed over 9 squared. Okay, as numbers, 3 cubed is 27 and 9 squared is 81. So when we simplify those, we're going to have a fraction of 1 over 3 left. And for the variables, x to the 12 over x to the 6, because 12 is bigger than 6, I'll move the x to the 6 to the top. So I'll do 12 minus 6 as my new exponent. So x to the 12 minus 6. Or I'm going to take this one and actually move it back to the top, which might seem kind of silly since I just moved it to the bottom, but it was easier for my brain to process it doing it that way. Okay, alternatively, we could have left it in the top and only moved the x to the 12 up there and then just done this in one step, but I think it's easier if you break it down this way. So now in my final step, I'm just going to simplify. 27 over 81 leaves a fraction of 3 on bottom and 1 on top, because 27 and 81 are almost the same number, really. 27 is just 1/3 of 81. So I can figure that out by dividing both the top and bottom by 27, and I'll get 27 divided by 27 is 1 on top, and 81 divided by 27 is 3 on bottom. And then x to the 12 minus 6 is just x to the 6. So I end up with x to the 6 over 3. All right, one more. This one's not so bad. We have a whole bunch of stuff on top, a whole bunch of stuff on bottom, and then a power 3 on the outside. What I'm going to do different here than in the other problems is because everything is raised to the power 3, I'm going to simplify the inside first and then worry about that exponent of 3. So on the inside, we have a 16 on top and a 4 on bottom. That's going to give me a 4 left on top. Okay. We have an x on top and an x on bottom. Those x's are just going to cancel each other out, so I'm not going to have any x's left. I'm going to write x to the 0 here just to make that clear. I think that'll be better because it's x to the 1 minus 1. So the x's cancel. Then we have y to the 7 over y to the 1. So that's going to give me y to the 6 left. And then z to the 5 over z to the 2 is going to give me z to the 3. So simplifying that now, we have 4y to the 6 z to cubed, all to the power 3, where I got rid of the x to the 0 since that's just 1. Okay, that x to the 0 just cancels. And so now all we have to do is distribute that 3. 4 to the power 3 is 64. Y to the 6 to the power 3, we multiply the exponents to get y to the 18. And z to the power 3 to the power 3 is z to the power 9, where we just multiply exponents again there. Wow, that was a lot. I think this was probably the hardest lesson we've had so far. So if you're struggling a bit, don't worry, I'm right there with you. A lot of math when we're dealing with rules of exponents. The key is just to be careful and make sure that you have these rules we went over on the first page down, because all we're really doing is applying these rules over and over again, just in slightly different ways each time. But as long as you know these rules, these 5 rules on the front, every problem is just a matter of applying these rules in the correct order to make sure we get to the end result. All right, thanks for joining me, guys. I'll see you next time.